This starts chapter 9. In chapter 9, we're going to be evaluating the performance of gas power cycles for which the working fluid remains a gas throughout the entire cycle. And 2, we're going to develop simplifying assumptions applicable to gas power cycles. We're also going to review the operation of reciprocating engines as well as analyze both closed and open gas power cycles, and then solve problems based on the Otto, the diesel, and the Brayton cycle. So a little bit of an overview. Most power producing devices operate on cycles. So in general, these cycles are difficult to analyze. So to make the analysis feasible, idealizations are utilized. So in the ideal cycle is a cycle that resembles an actual cycle closely, but it's made up of internally reversible processes. So if you recall, the thermal efficiency of a heat engine is the ratio of the net work produced by the engine to the total heat input. And then the Carnot cycle has the highest efficiency of all heat engines operating between the same temperature levels. No cycle can be more efficient than the Carnot cycle. Ideal cycles are internally reversible, but unlike the Carnot cycle, they are not necessarily externally reversible. So as a result, ideal cycles may involve heat transfer through a finite temperature difference. The following idealizations and simplifications are commonly used or commonly employed in the analysis of power cycles. 1, the cycle does not involve any friction, so therefore the working fluid does not experience any pressure drop as it flows in pipes or devices. Number 2, all expansion and compression processes take place in a quasi-equilibrium manner. And number 3, the pipes connecting the various components of a system are well insulated, and heat transfer through the medium is negligible. Also, property diagrams. In the analysis of cycles, property diagrams such as PV and TS diagrams serve as valuable aids. Both on the PV and TS diagrams, the area enclosed by the process curves of a cycle represents the net work produced during the cycle, which is equivalent to the net heat transfer for the cycle. So on a TS diagram, heat addition proceeds in the direction of increasing entropy. Heat rejection proceeds in the direction of decreasing entropy since heat carries entropy away. The isentropic processes are represented by a constant entropy line. Carnot cycle. If you recall, the Carnot cycle is composed of 4 totally reversible processes: isothermal heat addition, isentropic expansion, isothermal heat rejection, and isentropic compression. The Carnot efficiency is the most efficient cycle that can be operated between a heat source at TH and a sink at temperature TL. So the thermal efficiency of a Carnot cycle can be represented as a function of the temperature of the sink and the temperature of the heat source. What's the value of the Carnot cycle? Well, reversible isothermal heat transfer is very difficult to achieve. It is not practical to build an engine that would operate on a cycle that closely approximates the Carnot cycle. So the value of the Carnot cycle comes from it being a standard against which actual and ideal cycles can be compared. The thermal efficiency relation conveys an important message that is equally applicable to both ideal and actual cycles, and it reads as the following. Thermal efficiency increases with an increase in the average temperature at which heat is supplied to the system, or with a decrease in the average temperature at which heat is rejected from the system. Right, so if I have the Carnot efficiency, 1 minus TL over TH, the higher the TH, the higher the efficiency, and the lower the TL, the higher the efficiency. Also, in gas power cycles, the working fluid, so we're going to go over something called air standard assumptions. And the air standard assumptions are the following. In gas power cycles, the working fluid remains a gas throughout the entire cycle. In all gas cycles, energy is provided by burning a fuel within a system boundary. The composition of the working fluid changes from air and fuel to combustion gases during the course of the cycle. So considering that air is predominantly nitrogen that undergoes hardly any chemical reactions in the combustion chamber, the working fluid closely resembles air at all times. So to simplify the analysis of gas power cycles, we utilize the following approximations, which are known as the air standard assumptions. So 1, the working fluid is air, which continuously circulates in a closed loop and always behaves as an ideal gas. Number 2, all of the processes that make up the cycle are internally reversible. Number 3, the combustion process is replaced by a heat addition process from an external source. And number 4, the exhaust process is replaced by a heat rejection process that restores the working fluid to its initial state. We're going to go over this in more detail in a little while. We could take this a step further and call it also cold air standard assumptions. And that takes the assumptions a step further, asserting that the air has a constant specific heats whose values are determined at room temperature, 25 C or 77 Fahrenheit. And an air standard cycle is a cycle for which the air standard assumptions are applicable, which are going to be a good chunk of the stuff that we're doing in this chapter. Okay, let's go ahead and let's do an example problem. An air standard cycle with constant specific heats at room temperature, right? So that would be cold air standard assumptions. So an air standard cycle with constant specific heats at room temperature is executed in a closed system with 0.003 kilograms of air and consists of the following 3 processes. Process 1 to 2, constant volume heat addition from 95 kilopascals in 17 C to 380 kilopascals. Process 2 to 3, isentropic expansion to 95 kilopascals, and process 3 to 1, constant pressure heat rejection to the initial state. We want to show the cycle on a PV and TS diagram, calculate the net work per cycle, and determine the thermal efficiency. So we're going to go ahead, and one major assumption that we're going to draw is that we are going to use cold air standard assumptions. So let's go ahead to the next slide and let's figure out part A, which is showing the process on PV and TS diagrams. So here's my PV diagram. And here is my TS diagram. So starting at state 1, I have a constant volume heat addition process to state 2. Right, so from state 1 to state 2, I have heat addition. Now remember that there's no saturation curve related to this. If you look at an ideal gas region, right, this is a saturated curve. The ideal gas region is like up here somewhere, right, and it's way in the superheated vapor region. So if I go ahead and take a graph in this way, that's where this graph comes from. Okay, so we're way in the superheated vapor region, which is way in this ideal gas region for air. So no need to draw a saturation curve. So again, process 1 to 2 is constant volume. And if I look here as heat addition, I'm going to have an increase in temperature as well as an increase in entropy due to heat addition. So that'll be process 1 to 2 in this direction with heat addition. Process 2 to 3 is isentropic expansion. So I'm going to be going ahead and expanding to state 3, where this is going to be work out to state 3. And over here, I would have isotropic expansion, so it would be constant entropy, state 2 to state 3 with work out. And then finally, state 3 to state 1 is constant pressure, heat addition. I'm sorry, heat constant pressure, heat rejection. So then the temperature would decrease and the entropy would also decrease, giving me my PV and my TS diagram. So then part B is asking you to calculate the net work for the cycle, right? So part B, how do I calculate the net work for the cycle? First thing I'm going to do is a first law around the cycle. If I do a first law around the cycle, I get energy in minus energy out equals delta E system. Delta E system is 0 because this is a cycle, so everything returns to the initial state. So the only energy transfer terms crossing the boundary would be the heat transfer terms and work. So I have energy in as Q in, energy out is work out and Q out. So my work out would equal Q in minus Q out. So if I'm going to compute this work out as a function of Q in and Q out, I need to do a first law analysis now around the process. So a lot of times when we're doing cycle analyses, you're going to have to vary the boundaries for which you do your first law. So the first one I did was do a first law around the cycle. Now we're going to move on to doing a first law around the process. So if I look at the two processes for the heat transfer processes, I have process 1 to 2 is heat in, and process 3 to 1 is heat out. So if I do a first law analysis for Q in, that is a constant volume heat addition. So I have E in Q minus E out, which is 0, equals the change in energy of the system. So I get that Q in is equal to mass times U2 minus U1. And for process 3 to 1, I get energy in, Q in, minus energy out. This is a constant pressure heat rejection. So there is going to be some change in volume, right? So, and it's at constant pressure, so it'll be P delta V. That would be the boundary work at constant pressure equals delta U. So in this case, my Q out will equal mass times, delta U plus P delta V, which equals delta H. So therefore, my Q out will equal mass times H2 minus H1. So with my analysis of the cycle, I first did a first law analysis around the cycle, then I did a first law analysis around the processes. Now that I did a first law analysis around the processes, the next step is to actually evaluate the properties in each state so that I can get U1, U2, and H3 and H1. So I actually made a mistake here. That should be H3 minus H1. So how do we do that? Well, let's start at one point to which you're given the properties, right? So if you remember back in the problem statement, state 1, they give us T1, which is 290 Kelvin. So what you want to do is go from T1. So what we're getting at now is evaluating the properties. Something I did forget, since we're using cold air standard assumptions, right? We would go ahead and approximate the heat in as CV delta T. So that would be CV T2 minus T1. And then we can also approximate Q out as MCP delta T, since it has to do with enthalpy, right? Enthalpy is For ideal gas, the change in enthalpy can be approximated as Cp delta T for constant specific heats, and for delta U can be approximated as Cv delta T for internal energy. And if you remember back at the problem statement, we're assuming cold air standard assumptions. Cold air standard assumptions basically means that your specific heat can be evaluated at room temperature. So with T1, I know T1, and I want to go ahead and get T2. So I'm going to go ahead and analyze the process from 1 to 2 is constant volume. So what I need to do is what I call follow the process line. If I want to get the temperature at T2, I follow from T1 to T2, which is constant pressure, or I'm sorry, constant volume. So if I go ahead and use the ideal gas law, right? Again, I pull on one side of the ideal gas law, everything that's changing, which is pressure and temperature. And on the other side, put everything that's remaining constant, which is R over nu. So that means that P1 over T1 equals P2 over T2. So I can use this to solve for T2 as P2 over P1 times T1. I have P2, I have P1, I have T1, I put it all in Kelvin, I can get T2 is 1160 Kelvin. So now that I have T1, I have T2, the next thing I need is T3. So I'm going to go back and I'm going to analyze. So for state 2, I found that the temperature is 1160 Kelvin. And now I analyze process 2 to 3. So I go from state 2 to state 3, which is isentropic. Right? So since the process 2 to 3 is isentropic, I need to find a relationship that allows me to use the assumptions that this is an ideal gas with constant specific heats undergoing an isentropic process. So if you recall, that would allow me to use the following correlation, that T2 over T3 equals P2 over P3 to the K minus 1 over K. Now, so happens that P3 is equal to P1, so I can actually calculate P3 pretty directly by making the substitution of P3 is equal to P1 here, and then I just calculate T3 knowing T2, and I get T3 is 840 Kelvin. Right, so again, if you take this step by step, what I did was first did a first law around the cycle, right, and I ended up finding my unknown as workout as a function of Q in and Q out. In order to get Q in and Q out, I need to go and to analyze the processes. So I went ahead and did a first law analysis on process 1 to 2 and 3 to 1, and ended up getting the Q in and Q out as a function of properties, or as a function of temperature, since it's constant specific heats. Then I need to go ahead and find the temperature at each state, starting at a state to which they give me the temperature, which is at state 1. I follow a process line from 1 to 2, from state 1 to state 2. That process is defined at constant volume. So I use the ideal gas law for a constant volume process to compute T2. Then to go from state 2 to state 3, that process is isentropic, so I have to find the correlation for analyzing an ideal gas undergoing an isentropic process with constant specific heats. So the trick is making sure that you follow the process lines and you understand how to associate the assumptions for the process with the correct correlation. Now that we have all these in, I can go ahead and compute my Qin as mCV T2 minus T1, and my Q out as mCp T3 minus T1. You plug in your numbers, get about 2.07 kilojoules for Q in, about 1.65 kilojoules for Q out, and then I can figure out that my work net is equal to Q in minus Q out, which equals 0.42 kilojoules. And then we can move on to the last part of the problem, which is part C. I'll go ahead and do it in this corner of the slide. So I get that thermal efficiency is equal to net work over Q in. So my net work is 0.42 and my Q in is 2.07. So my efficiency is approximately 20%.